So in this video, we're going to take the wine and music example and really try to walk through the procedure that we're going to use to perform this test. So first of all, let's talk about how we're going to treat this two-way table. What we're going to do is focus on the table, and you can flip back to page 850 and look at the original table with the counts in it, not the one with the conditional probabilities, but the one with the counts. And we're going to talk about the dimensions of that table. First of all, it's a two-way table because on the one edge or on the one side we have the type of music being played, and the other one we have the type of wine being purchased. And what we're really going to say is that this is what we call a 3-by-3 table. There are 3 rows and there are 3 columns. So we do not include the totals, so no totals. Just the counts themselves of the types of wine sold when the music is playing. And each one of those numbers is going to be considered a cell in this particular distribution. And the reason that matters to us, that the first number represents rows, second number represents columns, is some of our formulas are going to come back to that R and C business. So we're going to come back to that. Well, first of all, let's talk about some hypotheses here. Obviously, we need to come up with a way to state a hypothesis, and what would we do, and how would that even be phrased? So essentially what we would start with, of course, in the hypothesis is to say that there is no difference between the different types of music, that when you play no music, or when you play French music, or when you play Italian music, that there's no difference in that. There's a pretty good example if you look at page 854. At the very top of the page, example 14.5, they first of all identify the 3 populations at work here. Population number 1 is the wine that's sold with no music. So that's the first population that we have. And of course, those bottles are different. They don't cross over at all because either you're playing no music or French music or Italian. There's no crossover. These could be on different days, different weeks. We're not sure how they randomized it, but essentially that's what we got. Population 2 is when the wine is sold when there's French music playing. And population 3 is the bottles of wine that are sold with the Italian music playing. And it's reasonable for us to say that the best way for us to make a null hypothesis is to say there's no difference in the proportion of each type of wine that's being sold with these different types of music that are playing. And on page 854, that's exactly how the null is stated. It says the proportions of each type of wine sold are the same in all 3 of these populations. So the music makes no difference. Remember that we always state the null as no difference, no change, and then we gather evidence for the alternative. So at this point, our next job is to try to say, okay, well, what would we have expected if that were true? In this particular case on page 854, we get a process that we're going to use for that. We're going to say that our expected count for any cell is going to simply be the row total times the column total divided by n. And in this case, we're gonna do this calculation for a couple of different cells as it's shown on this page. You can imagine that we have to repeat this. We need to do this 9 times. And each one could be slightly different depending on where we are, because for each row and each column, there's a unique total that's being used. Now on the bottom of page 854, they repeat the same table so you can see it again. So take a look at that particular table and notice that each row and each column has a total that's listed. So let's imagine for just a minute that we have some particular cell that we are interested in. So for example, we could have the total, let's put the French wine, and let's put the Italian wine, Italian, and let's put the other, and then as you know we have none. Across the top here we have French wine French music, excuse me, or we have Italian music, okay? And so, for example, this 30 right here represents the number of French bottles sold when there's no music playing. Well, that's 30 out of a possible 84 in this direction, and that's 30 out of a possible 99 bottles of French wine that were sold total with all the different types of music playing. So the expected value is going to have something to do with those numbers. It's also going to relate to the total number of bottles sold, which is in the bottom corner, which is 243. So basically, to get this expected value for this to compare to this 30, it's going to involve the row total, 99, the column total of 84, and the total for the whole table, which is 243. Now, they give us an example for that particular calculation on page 855, and you'll notice they take the 99 times the 84 and divide it by the 243, and when they do that, they get 34.222. So it's the row total, 99, times the 84 divided by the 243, and that is going to go in this cell right here for the expected counts. So if you'll notice on the next page, on page 855, they have the expected counts. In the upper left-hand corner is that 34.222 that we just saw calculated. Let's repeat that for the Italian one that's right below it and see where they get the 10.716. So what would they use for that? Well, what's the row total for the Italian? Well, the row total for the Italian is 31. The column total is the same, 84. And if you divide that by 243, we should get that same 10.716. So let's see what we get. 31 times 84 divided by 243, that's equal to 10.716. Stop the video for just a minute. Choose some other cell, doesn't matter which one, and make sure that you can generate the number in that cell. When you finish that, go ahead and start the video over again. Assuming that you're able to get the expected value of another cell or two, you probably have an idea what's going on. What we're going to do before we move on to the rest of the chi-square test is it's actually really important to be able to get these expected values correctly. So we're going to take a look at one exercise before we move on to the wine example, and that's problem 11. It's at the bottom of page 855, so it's right where we are. And so what we're trying to do here is get a sense of if I have several different treatments available for a particular addiction, in this case nicotine, which one works the best? So what you have listed at the top of page 856 is you have a table there, and it talks about the treatment. One option is a nicotine patch, one option is a drug, one option is both the patch and the drug, and one is essentially a placebo. And you might notice that there are a different number of subjects in each group, and you're given the successes, and you'll also notice that that's all you're given. Part A asks us to summarize these data in a two-way table, and you might think, well, don't we already have that? We have different columns and rows, so aren't we done? But really what they give you when they give you the subject total is they're giving you the totals. They're not giving you something to compare to successes. So what other category would you fall into? Well, if success is defined as not using nicotine a year after treatment, then the only other option that we could have here is to say, well, what about the failures? So what we really need to do is we need to have something to compare the successes to. How would I calculate the failures? Well, I'd take the number of subjects who succeeded, subtract those out from the total, and that would give me the failures. So for example, in the first one here, it'd be 244 minus 40, or 204. For the drug, the same procedure would give us 170 failures, 158 failures, and 135. It's tough to compare these numbers directly top to bottom, although if you'll notice, this one, the patch plus the drug, seems to be, even though it's also the highest total, it looks like it's got a pretty favorable proportion when compared to failures. In Part B, we're asked to actually calculate these as proportions so that we can compare them a lot more effectively. So you'll notice in Part B, if we make a proportion of 40 to 244, that actually gives us a proportion of 0.16. The proportion for the drug, 74 divided by 244, would give us a 0.30. The patch plus the drug, 87 out of 245, would be 0.36. And the placebo is 0.15. Or actually 0.16, excuse me, rounded off. So these proportions show, interestingly enough, that the patch and the placebo, patch alone and the placebo, don't seem to have that much of an effect. But when you combine the patch and the drug, we start to get actually an increased effect. So it's kind of interesting how the patch seems to work more effectively when used with the drug. And that gives us an idea of how we might create our null. Part C asks us to make a graph. So what kind of graph could we make? Well, an obvious one could be a bar graph in this case. We're not going to take the time to make that, but we certainly could, probably with the proportions, to show how the highest bar here would be the patch plus the drug when showing successes. In Part D, we're asked to sort of talk about, in words, what would our null mean that all these proportions were the same? Well, it would simply say that the success rate is the same for all 4 treatments. And we could write it that way as our null hypothesis. Now we want to find the expected counts. Notice they're counts, not percents, if the null is true, and display them in a two-way table. So this is where we get to practice that. Stop the video and see if you can convert this two-way table into an expected count table, and then start the video again when you're done to check your work. So here's the table, and you'll notice that the expected counts for the successes for the patch and the drug are the same, and the expected number of failures are the same. Kind of makes sense if you think about it, because we have the for the successes and failures, those numbers were the same anyway, and so as between the patch and the drug. And so when we look at the row and column totals, it's going to make sense. If you are having a little trouble coming up with these numbers, let's just see how one of them is calculated. Let's look at this top left-hand corner and where that number would have come from. To get 61.75, we would take the row total times the column total and divide by the total in general. The row total there would be the 244 that represents the number of people who were taking the nicotine patch, times the column total, that would be the total number of successes, which would be 266, or 226, excuse me, divided by the total number of subjects, which is 893. When you divide those out, you get 661.75 as the top corner. In the next row, you had the same number of subjects taking the drug, and so in that case, again, the successes stays the same, and then you divide by the same number of subjects. So that's why you get the same number for those two in a row. In problem part F, it asks you just to compare the tables of observed and expected counts. And in that case, if you look at the number of smokers who successfully quit with the patch plus the drug and the drug, they're higher than what we would have expected according to the calculations we just did. We got an 87 who were in that category where we only expected to have about 62. And so again, that is not surprising to us in terms of saying, okay, it was higher than expected. The placebo numbers are lower than expected. And so what we're going to see down the road is we're going to say, you know, are those differences big enough for us to draw a conclusion? And that's what we're going to see in the next part of the video when we calculate a chi-square statistic that goes with this sort of test, is we're going to try to quantify what these differences are. So now you're ready to go to video part 3.